Okay, students, I am going to start. Actually, the PPT I tried, but I was unable to explain by using that PPT due to some problem. Now I am going to continue the class. Right? You listen very carefully. Right. Manually, I will explain by using this board atoms chapter. Right? You listen. We are going to start the atoms chapter. Okay. The chapter name is atoms. Atoms. Okay. It is very easy and interesting chapter, and that I am going to start with. Okay, is it my voice clear? I think. Na? Yes, now I am going to start the atoms chapter. In this first, I am going to explain the Rutherford atomic model and later, first J. Thomson atomic model I will explain. Later Rutherford model. Okay, and little bit we will discuss today. Right, I am going to continue. You listen very carefully, and from this chapter, I think nearly you will get the 3 marks or the maximum you will get the 5 marks. There is no fixed weightage for this chapter, right? And now, what is J. Thomson model and what he explained? Okay, first I am going to start the J. Thomson model. J. Thomson model. J. Thomson atomic model. What is this? J. Thomson atomic model is what? According to J. Thomson atomic model, right? It was very simple. That is according to the J. Thomson atomic model. According to J. Thomson atomic model, I think no need to give the notes. Directly I will explain because already I made the PPT for that. I will post it. Okay. According to J. Thomson atomic model, what he said? He said that the positive charge of entire atom is distributed like seeds in the watermelon. Okay. Sorry, the positive charge of atom is distributed in the whole atom uniformly. Positive charge is distributed throughout the atom uniformly, and but the negative charged particles are embedded like seeds in the watermelon. This is the J. Thomson model. What he said, I will explain once again. Okay, according to the J. Thomson model, what about the positive charge? The positive charge is uniformly distributed throughout the atom. The positive charge is uniformly distributed throughout the atom. Positive charge uniformly distributed throughout the charge. Uniformly distributed throughout the charge. Sorry, throughout the atom. Positive charge. Actually, atom is made up of electrons and protons. Firstly, J. Thomson don't know about these electrons and protons, but here he explained the structure of the atom. That atom consists of positive charge and negative charge, but the positive charge is uniformly distributed throughout the atom, but the negative charge, that negative charged particles are embedded like seeds in the watermelon, like seeds in the watermelon. Don't note the notes. Okay, and I will send that PPT. Okay, right. Then you look at here, and this is a watermelon. You see here, in the watermelon, if you will cut halfly, then there is a matter will be there, right? Red color, and that red color matter is considered as the positive charge. The positive charge is distributed in the entire atom, but the negative charged particles like this, there are some negative charged particles are there in the atom. That negative charges are distributed like seeds in the watermelon. Okay, this entire one is the positive charge. Okay, the entire one is the positive charge, but the negative charged particles are embedded like seeds in the watermelon. This is the J. Thomson model, and this we can also say that it is a plum pudding model. Okay, plum pudding model. because it is based on the watermelon they are explaining. Okay, and next, limitations are what? What are the limitations of this atomic model? What are the defaults? What are the demerits of this model? That is, it could not explain the origin of spectral lines. Why spectral lines are formed, he not explained, right? Origin of spectral lines not explained by using J. Thomson model. And one more point he not explained, that is, it could not explain the scattering of alpha particles. Why scattering is occurred by large angles? Okay, scattering of alpha particles also not explained. And the next one is the Rutherford atomic model. Okay, what is the Rutherford atomic model? And before going to Rutherford atomic model, we have to discuss about Rutherford alpha scattering experiment. Rutherford alpha scattering experiment. What is the Rutherford alpha scattering experiment and what it explains? According to the Rutherford alpha scattering experiment, okay, and there is a one source he took. This is the source of the alpha particles. What are alpha particles? S is the source of alpha particle. Source of alpha particle. What is alpha particle? Alpha particle means double ionized helium atom. Helium plus plus. Okay, what is the charge of alpha particle? Charge of alpha particle is plus 2e. Okay, charge of alpha particle is plus 2e because two electrons are removed. The mass of alpha particle is 4 units because we take the mass number as mass 2 helium 4. This mass number we can take as a mass. This is the source of alpha particles, and here we are placing the two lead bricks. These are the two lead bricks, lead plates. They are made with the lead. Okay, and here we are placing the thin gold foil. This is a gold foil. Okay, this is the gold foil. Okay, and here we are placing one circular screen. Okay, zinc sulfide screen it is, zinc sulfide screen. Okay, and now here we will place one detector. This detector is movable on the screen. Okay, now what happens at here and how the experiment will be there, you listen it here. From the source, the alpha particles will starts, and they are collimated, means they are made a narrow beam by using lead bricks, because they will, these alpha particles, these alpha rays, okay, they will go, these alpha particles are the double ionized helium atom. Double ionized helium atom is called as alpha particle. Means if two electrons are removed from the helium atom, then it is called as alpha particle. That alpha particle will go in the straight, okay, and it is made, it is collimated, means made narrow beam, narrow beam. Okay, for example, it is just like this there, like this beam it is coming, alpha particles are coming, and through this gap only alpha particles travel, then it is made narrow beam by using this lead bricks. Okay, and this narrow beam is allowed to incident on the gold foil. Okay, and then they observed something, that some of the alpha particles will scatter like this, and then they will detected by the detector. This is a detector. Okay, and then alpha particle may be scattered this side or this side, different directions alpha particles will scatter. Some alpha particle may be come back like this, right? And then this is the scattered alpha particle. Okay, scattered alpha particle. Then what happening at here, by rotating the detector we can find how many alpha particles scattered at this angle. Okay, at here how many alpha particles came, right here how many alpha particles came. Then to know that, we have to use the detector to know the number of alpha particles scattered in particular direction we can find out. Okay, this is the Rutherford alpha scattering experiment and what he observed in this experiment. Once again you listen carefully. S is the source of alpha particles. That alpha particles emitted from the source. Okay, and there passes through the gap between the lead plates, and these gap makes the narrow beam of alpha particle. it is allowed to incident on the gold foil. Then after that, through the gold foil, when alpha particle passes, then they will be scattered. What is the meaning of scatter? When alpha particle is going along this direction, but due to any reason, if it's deviated from its original path, this is the deviated, okay, alpha particle, and this is the original direction of alpha particle. Originally the alpha particle is trying to go this side, but due to some reason it is going this side, and the angle through which it is scattered, it is bends from its original path. It is called as the angle of scattering. The theta is the angle of scattering, and this is said to be scattered alpha particle. It is a scattered beam, and this is the incident beam, and this angle is called as the angle of scattering. Here, for example, this is the original direction, and this is the angle through which the alpha particle bends from its original path, right? That angle is called as angle of scattering. But we cannot say that alpha particle scattered only in this direction. Alpha particle may be scattered in any direction, right? That's why we are keeping the detector on the circular scale. The circular scale is movable. Circular scale is movable. We can keep the circular scale at here. We can keep the detector at here. Detector is movable on the circular scale, not circular scale, sorry. Detector is movable on the circular scale, and we can keep the detector at a particular position, and we can find out how many alpha particles are scattering along this direction and how many alpha particles scattered along this direction. Like this we can find out. And this Rutherford alpha scattering experiment is actually did by the his students, that is whose name is Geiger and Marsden. Actually this setup is made by the two scientists. They are also scientists, okay. At the age of 20 years only they did this one, okay. Geiger Marsden, okay. This is experimental setup is done by the Geiger Marsden, okay, under the suggestion of the Rutherford, okay, right. Now, what he observed in this Rutherford alpha scattering experiment? In Rutherford alpha scattering experiment, what they are using? Alpha particles they are using. What is the charge of alpha particle? Can anyone give? What is alpha particle? Alpha particle is the 2 helium 4, right? But it is doubly ionized. Doubly ionized means two electrons are removed. That's why its charge is plus 2e. Okay, its charge is plus 2e. Its mass is what? Mass of alpha particle is, we take the mass number is 4 units, okay. This is alpha particle, okay. Alpha particle is positively charged. Now alpha particle, what they observed, Geiger Marsden are the students of the Rutherford, and they did the experiment based under the suggestion of the Rutherford. Now let us see here. Now what he observed in this experiment, that is alpha particles are some observations and conclusions I will explain, okay. Observations and conclusions, what they observed and what they concluded. That is, the first observation is that most of the alpha particle most of the alpha particles, what they did, most of the alpha particles are passes straight without any deviation, okay. Passes straight through the gold file without any deviation, okay. Through the gold file, what they observed, that most of the alpha particles travel straight without any deviation through the gold file, okay. You see here the picture, alpha particles are traveling it here, and most of the alpha particle traveled straight. See the गया हुआ, deviate नहीं हुआ, bend नहीं हुआ, scatter नहीं हुआ. इसका क्यों नहीं हुआ, scatter क्यों होता है actually? That is, you see here, actually what we are doing it here, this is the alpha particle, and we are throwing the alpha particle towards the gold file, right? And most of the alpha particles travel in the straight without any deviation, okay, through the gold file. Gold file means thin layer of the gold, okay. And then that most of the alpha particle travel in the straight without any deviation. I mean, they cannot scattered. Why they are not scattered? When they will scatter, alpha particle has positive charge. If any positive charge is there, that will repel. Okay, if this alpha particle is positive charge, like this it want to go. If any positive charge is there in the gold file, that positive charge repels this positive charge alpha particle, then due to that the deviation will occurs. Okay, but here most of the alpha particles are scattered. Most of the alpha particles are not scattered, they travel in the straight line without any deviation. By that they concluded that most of the atom is hollow. most of the atom most of the atom is hollow means empty. Most of the atom is empty. For example, you say take this as an atom. This is the gold atom. Okay, gold file में gold atoms होता है. Nucleus is very small size. Nucleus is very small size, positive charge. But alpha particle, if it is goes like this, okay, it can travel in straight. For example, this is alpha particle. It can go in the straight like this, and this is also alpha particle. Right? It can travel in straight, and it can travel in the straight like this. Most of the alpha particles are traveling straight without any deviation through the gold file. This is the gold atom we will take. Okay, gold atom. Inside the atom at the center, little nucleus will be there. Okay, and most of the atom, for example, if positive charge is completely distributed in the atom according to J.J. Thomson. For example, if you assume that J.J. Thomson, according to J.J. Thomson, positive charge is uniformly distributed throughout the atom. If positive charge is distributed uniformly throughout the atom, then what happens? You tell this alpha particle also repelled by this positive, it can bend. This alpha particle also repelled by this positive, it can bend, and all the alpha particles should scattered. But practically, what happening? Practically, most of the alpha particles go straight without any deviation. That means positive charge not distributed throughout the atom. Positive charge not distributed throughout the atom. J. Thomson one is wrong, right? Now, most of the atom is hollow. Most of the atom is hollow means empty. Okay, according to Rutherford. Next, second observation is what? The second observation is that very simple observation, right? And he observed that only 0.14% of alpha particles, only 0.14% of incident alpha particles, 0.14% of incident alpha particles are scattered more than 1 degree, are scattered more than 1 degree. How many alpha particles scattered more than 1 degree? Only 0.14%. Means what? Out of 100 alpha particles, only 0.14 alpha particles. Okay, that means, for example, you multiply this one nearly. If you multiply with 10, you will get 1.4. Right? If you will, what I am telling it here, 0.14% of alpha particles scattered with an angle more than 1 degree. 0.14% means what? 0.14 means 0.14 for 100. Out of 100 alpha particles, 0.14 alpha particle scattered with an angle more than 1 degree. If you multiply this one with 10, then 100 become 1000. This one 0.14 become 1.4. Means out of 1000 alpha particles, one alpha particle scattered at an angle greater than 1 degree. And this they observed. That means most of the alpha particles scattered with passes without scattering, right? And the next one is next observation about one alpha particle. Okay, about one alpha particle out of 8,000. Okay, one alpha particle in 8,000 alpha particles. Okay, 8,000 alpha particles, 8,000 incident alpha particles scattered scattered more than 90 degree, more than 90 degree. How many alpha particles scattered more than 90 degree? More than 90 means what? You see, alpha particle is coming this side. Okay, this is alpha particle initial direction, this is the original direction. If it is scattered like this, you see, then the what is the scattering angle? This is the scattered alpha particle. Okay, this is the scattered alpha particle, this is the original path. And how much angle it will bends? It bends more than 90 degree, right? Then like this, how many alpha particles is scattered? Only one alpha particle out of 8,000, out of 8,000. If 8,000 alpha particle incident on the gold file, in that only one alpha particle scattered with an angle more than 90 degree. More than one, okay, 1,000 में एक more than 1 degree scatter कर रहा है, 8,000 में एक more than 90 degree scattered कर रहा है. Okay, and based on these points, based on these points, they concluded something. Based on this Rutherford experiment, they estimated the size of the nucleus. Okay, based on this, they estimated the size of the nucleus. Most of the alpha particles are traveling without scattering. That means most of the atom is empty. Now I am going to explain one point. That is how he estimated the size of the nucleus. What is the reason for the scattering? Can anyone tell what is the reason for the scattering? Why some of the alpha particles are bending while passing through the gold file? Anyone can type the message. Why alpha particles are some of the alpha particles are scattering? Why some of the alpha particles are scattering? Is it clear, students? Is there any problem? Anyone can type the message. I was unable to see your chat box. I think today getting this trouble. Okay. Estimation of the size of the nucleus. He estimated the size of the nucleus. How they estimated the size of the nucleus? That is, actually, you know that size of atom, size of nucleus, size of nucleus means size means radius. Okay, size means radius. Okay, that is in the order of, okay, the radius or the diameter, size of the nucleus. Size means we take it as a radius or diameter we can take as the size, and the size of nucleus is in the order of, size of nucleus is in the order of 10 to the power of minus 15 meters to 10 to the power of minus 10 meters. This is the size of the nucleus, very small, 0.00000 like that we have to write. This is the size of the nucleus. is range from 10 to the power of minus 15 meters to 10 to the power of minus 14 meters. 10 to the power of minus 14 meters, not 10 to the power of minus 10. It is 10 to the power of minus 14 meters. Okay, but the size of atom is how much? Size of atom, size of atom is in the order of 10 to the power of minus 10 meters, right? That means size of atom is very much greater than the size of this. If this is nucleus, if this is nucleus, then this is the atom. This is the atom, right? Atom size is very much greater than the nucleus size. Nucleus is the point size. Okay, and now what about the size of atom? How many times of the size of nucleus? Size of atom, okay, size of atom, you multiply size of nucleus with 10,000. This is multiplied with the 10,000. Size of atom is, okay, if you multiply with the 10,000, you will get this one, right? And size of atom is 10,000 to 10,000 to 1 lakh, 1 lakh, 1 lakh times of 1 lakh times of size of nucleus. Size of nucleus, that much less will be their nucleus size. Okay, the size of atom is 10,000 to 1 lakh times of size of nucleus. You see here, this 10 to the power of minus 14 is the size of the nucleus. For example, you consider the 10 to the power of minus 14 is the size of the nucleus. Atom size is what? 10 to the power of minus 10. You multiply atom size with nucleus size with 10,000. When you multiply nucleus size is what? I am taking the nucleus size as 10 to the power of 10 to the power of minus 14 meters. Nucleus size I am taking as 10 to the power of minus 14 meters. If it is multiplied with 10,000, we are getting the 10 to the power of minus 10. Is it right? That means atom size is 10,000 times of nucleus size. Or if you take the nucleus size as 10 to the power of minus 15, if you take the nucleus size as 10 to the power of atom size is equal to, okay, nucleus size I am taking the 10 to the power of minus 15 meters. Atom size is 10 to the power of minus 10 meters. Then this is multiplied with the 1 lakh. Nucleus size is multiplied with 1 lakh, then you will get this one. 1 lakh means 10 to the power of 5. 10 to the power of 5 and 10 to the power of minus 15, you will get 10 to the power of minus 10. That means nucleus size. Okay, right? If nucleus size is multiplied with 1 lakh, then you will get the atom size. That means size of atom is 10 to the power of 10,000 to 1 lakh times of the size of nucleus. Okay, right. Next one is Rutherford nuclear model. Rutherford nuclear model. Rutherford nuclear model. What he explained? Rutherford nuclear model. Rutherford nuclear model is that based on alpha scattering, he explained the Rutherford explained some points. That is, the first point is that entire positive charge and most of the mass of atom concentrated at the tiny central core of the atom. Okay, what concentrated the tiny core of the atom? Entire positive charge and most of atom, most of at mass of atom, most of mass of atom, where it concentrated? It is concentrated at the center of nucleus, the center of the atom. Entire positive charge and most of the mass of atom are concentrated at the tiny central core of atom. At the tiny central core of atom. Okay. And the second point is that he observed, that is, the electrons are revolving. The electrons revolve, revolve around the nucleus in various circular orbits. Around the nucleus in various circular orbits. Like planets revolve around the like planets revolve around the sun. And the next point is that third point I'm going to explain. That is about the size of the nucleus, right? Size of atom is what? 10,000 to 10,000 to 1 lakh, 1 lakh times of size of nucleus, right? Next, what are the drawbacks of this Rutherford model? Drawbacks I am going to explain. Drawbacks is the first one. The drawbacks is that according to classical theory, what happens? According to classical theory, when electron revolves around the nucleus, when electron revolves around the nucleus, okay, this is the nucleus. When electron revolves around the nucleus in particular orbits, and at that moment, what happens? It should lose its energy continuously. According to classical theory, any moving object should lose their energy. Then that's when it loses the energy, then what happens? Then it should go in the like this, like this, like this, and it will fall in the nucleus. It should not continue in the same circular orbit. And when the electron falls in the nucleus, this is the nucleus at the center. In this path, it will go and it will fall in the nucleus. When the electron falls in the nucleus, the atom should be collapsed. But the practically atom is stable. Okay, that why he not explained. And the second one, okay, he not explained why atom is stable, right? Why atom stable? Why electrons are revolving in particular orbits? Okay, atom is not collapsing. And the next one more point, according to him, when the electron revolving in the particular orbit and releases losses the energy continuously. When continuous energy losses, then on the spectrum you should get the continuous bands. On the spectrum you should get the continuous bands. Continuously brightness should be formed. But actually on the spectrum we are observing the discrete bands. Why discrete bands are observed? That is not explained by Rutherford. This is about Rutherford atomic model drawbacks. Okay. Today I think little disturbance is there, and I am going to close the today's lecture. We will discuss clearly in the next topic. Okay. Right. Thank you to all.